Hello guys, how's it going? Mike coming back at you with another video on precalculus. In the previous video, we talked about division of polynomials, and we learned two methods which we can use to divide polynomials, either long division or synthetic division. In this video, we're going to take a little detour back to a couple videos prior. We're going to talk more about roots of polynomials. How can we find them? How can we narrow down possibilities? And what can these things look like? How many negative or positive roots can we have as well? So as you can see, we're very interested in finding roots of polynomials, but how can we narrow down the possibilities? Well, we can at least start by narrowing down the possibilities of rational roots or whole number roots. And we do this with a theorem called the rational zero theorem. What the rational zero theorem says, if you have a polynomial, a sub n times x to the n plus a sub n minus 1 times x to the n minus 1, so on and so forth, if that thing has integer coefficients, and if you are going to have a rational zero in the form p over q, then p is going to be a factor of the constant term, specifically the a naught, and q is going to be a factor of the leading coefficient, aka the a sub n. So in general, we just sort of represent all possible rational zeros with the following formula, if you will. All possible rational zeros, or as you'll see me use for short, PRZs, are of the form factor of the constant divided by factor of the leading coefficient. So let's try a couple sample problems here, see how we would use this. So we're going to find all possible rational zeros of this guy right here, 5x to the fourth minus 3x cubed plus 2x squared minus 7x plus 4. Now, just as a quick note before we continue on with this problem, it doesn't matter if we're missing any terms in the middle here. We could have not had an x cubed, or we could have not had an x term, but as long as you have the highest power of x and you have the constant, that's all you need to figure out possible rational zeros. So as we said, factor of the constant divided by factor of the leading coefficient. So all the factors of 4. You can have 1 and 4 or 2 and 2, but don't forget the negatives you could have. You could also have -2 and -2 or -1 and -4. Factors of the leading coefficient 5, that is plus or minus 1, as well as plus or minus 5. So we write plus or minus 1, plus or minus 2, plus or minus 4, all over plus or minus 1, and plus or minus 5. We do want to write out all the possible combinations that doing a number on the top divided by a number on the bottom could leave us. So how you do that, go with the first number you see on the top, and then go first over first, first over second, you go first over third, just first guy on top over everything on the bottom. Then you move on to the next number on top, and then top number over each thing on the bottom. Bam over bam, bam over bam. And then lastly, bam over bam, bam over bam. So when we do that, we're going to get 1 over 1, which is 1, 1 over 5, 1/5, 2 over 1 is 2, 2 over 5, 2/5, 4 over 1, 4, and then 4 over 5, 4/5. And we do want to include the plus and minus. If you forget to include the minus in there, you're leaving out half of the possible rational zeros that you could have. So you do want to make sure that you're always writing plus and minuses here. So try this guy on your own. See if you can come up with all possible rational zeros of 6x to the 7th plus 8x to the 6th minus x cubed plus 5x squared plus 9. So pause the video here. Once you think you have the answer, press play, and we'll see if your answer was correct. All right, so let's see if you are correct. We need all the factors of the constant divided by all the factors of the leading coefficient. Factors of the constant term, plus or minus 1, plus or minus 3, and plus or minus 9. Factors of the leading coefficient are plus or minus 1, plus or minus 2, plus or minus 3, and plus or minus 6. So we're going to have several possible combinations here. We have 1 over 1, which is 1, 1 over 2, 1 half, 1 over 3, 1/3, 1 over 6, 1/6. We have 3 over 1, 3. We have 3 over 2, 3 halves. We have 3 over 3, but that's 1. We already wrote that, so we're not going to rewrite that. And then we have 3 over 6, or 1 half. Already had that, not going to rewrite that. Then 9 over 1, 9. 9 over 2, 9 halves. 9 over 3 is 3. Already had that written there, so not going to repeat that. And then we have 9 over 6, or 3 halves. Again, already had that. Not going to write that once again. So these are all the numbers we have. And then, again, it is plus or minus to show that both the positive and the negative number is a possibility for your root. So what about roots that are not rational or complex valued roots as well? Well, a polynomial of degree n has, including multiplicities, n roots. These roots could be integers, they could be rationals, they could be irrational, they could be complex numbers. Whatever they are, a polynomial whose degree is n is going to have n roots. Now, if you have imaginary or complex roots, they're always going to show up in pairs. So if a plus bi is a root of a polynomial, then a minus bi is going to be a root as well. Those things always show up in pairs. And then if f of x is a polynomial of degree n, as long as n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex answer. Now, all real numbers are complex numbers, so whether your root does involve an I or it's just a real number, it is a complex root. And this theorem is called the linear factorization theorem. If you have a polynomial, as we see right here, then we can write this as a sub n, our leading coefficient, times the product of linear factors, times the product of x minus c1 times x minus c2 times x minus cn, where each of these c's are the roots, or the solutions, or the zeros. These are complex numbers, possibly real numbers, and they could possibly equal each other, some of them being equal, some not, or they could all be the same. Who knows? That will vary. But if you're given the roots of a polynomial, and you're given a point that the polynomial satisfies, you should be able to essentially construct the polynomial. So here's an example of how we would do that. You may see this on your homework or on a quiz or test. Find the polynomial f of x such that f of 2 is equal to negative 78, and f of x has roots positive 5 and plus or minus, plus and minus, I should say, 3i. So from that factorization theorem, and given our roots, we know that so far this thing has to have this form right here. There's some leading coefficient that we don't know of yet, but the but the factors here have to be x minus 5, x minus 3i, and x plus 3i. Because these are the zeros or the roots of this polynomial f of x, x minus that root is going to be a factor. So this is what it looks like so far. If we FOIL these things together, we are going to come up with a sub n times x cubed minus 5x squared plus 9x minus 45. Note that the x minus 3i and x plus 3i multiply to x squared plus 9 because I squared is negative 1. Here's where we use that point that we were given to figure out what the leading coefficient is, what that a sub n is going to be. So if I substitute 2 in for x in here, and I set this thing equal to negative 78, I can solve for a sub n. So 2 cubed is 8, 2 squared is 4, times 5 is 20, 9 times 2 is 18. So I have 8 minus 20 is negative 12, plus 18 is 6, minus 45 is negative 39. So negative 39 an is equal to negative 78. If I divide both sides by negative 39, I find that a sub n is 2. So I take this value of 2, I substitute it back in, right here, and I come up with my final polynomial. It gives me 2x cubed minus 10x squared plus 18x minus 90. So not too bad there. Now, how many positive real roots could we have, and how many negative real roots could we have? This is not guaranteeing it's a specific number of each. It's just telling us what the possibilities are. And how we do this is through the use of Descartes' rule of signs. And what it says is you have some polynomial, our typical standard form, with real numbers as coefficients, but we're going to be sticking with whole numbers as our coefficients here. The number of positive real zeros of f of x is equal to the number of sign changes in f of x. And I'll clarify that by saying it's the number of sign changes in the terms in f of x. It's equal to that number or less than that number by a multiple of 2. So to clarify here, say that there were 5 sign changes in our function f of x. The number of positive real zeros is either 5 or it's less than that by a multiple of 2. So it could be 2 less than 5 or 3, or it could be 2 less than that, which would give us 1. Obviously, you can't have a negative number of zeros, so once you hit the negatives or you hit 0, you stop there. But that's the number of positive real zeros. That's how many you could have. The number of negative real zeros of the given function f of x is equal to the number of sign changes in f of minus x, or again, the number of sign changes in the terms in f of minus x, or it's less than that by a multiple of 2. So to figure out the number of negative real zeros, we're going to need to do a little bit of work, and then we'll come up with that second piece of information that we need. But we're going to go through a sample problem here. We're going to see how this works. So we're going to find the number of possible positive and negative real zeros of this function here. X to the 7th minus 4x to the 6th minus 3x to the 4th minus 2x squared plus 7x plus 9. So first we're just going to look at the number of sign changes that occur in the terms in f of x here. This is really a plus that's happening here. So I'm going from plus to a minus. That's one sign change. Minus to a minus, there's no change. Minus to a minus, no change. I see I'm going from a minus to a plus, so there's a second change. And then plus to plus is no change there. So we have two sign changes in the terms in f of x here. So, since there are two sign changes in f of x, the number of positive real zeros is either 2, that number of sign changes that we saw, or it's less than that by a multiple of 2. Well, the only other multiple of 2 that is less than 2 and could still be possible is 0. So there's either 2 positive real zeros or there's none. That's the easy half of this, finding the number of possible negative real zeros. It's a tongue twister. Try saying that 5 times fast. Finding the number of possible negative real zeros does take a little bit more work to do beforehand. To do that, we're going to need to find f of minus x. So I'm going to take this function, f of x here, and anywhere I see an x, I'm going to substitute in a minus x. So f of minus x is minus x to the 7th power, minus 4 times minus x to the 6th, minus 3 times minus x to the 4th, minus 2 times minus x squared, plus 7 times minus x, plus 9. Now, as a sort of quick recap of properties of exponents, for those of us who have forgotten, I'll give you the short version of it for now, for the sake of solving this kind of problem. If you're raising minus x to an odd power, then you're going to have a minus sign left over. If you're taking minus x and you're raising it to an even power, there is not going to be a minus sign left behind. So minus x to an odd power, minus sign gets left behind. Minus x raised to an even power, no minus sign left behind. So when you simplify this all out, you get minus x to the 7th, minus 4x to the 6th, minus 3x to the 4th, minus 2x squared, minus 7x plus 9. This guy was raised to an odd power, so no minus sign there. There's a minus sign. This guy was raised to an even power, no sign change. Raised to an even power, no sign change. Raised to an even power, no sign change. Negative x raised to the 1, that's an odd power, sign changes. Plus here, minus here, and then the constant remains the same. Now we're going to look at the number of sign changes that occur in this guy right here. Minus to minus, no change. Again, no change. Again, no change. Again, no change. But we do have one change there, the minus to the plus. So since there is only one sign change in f of minus x, then we know that there has to be one negative real zero. And this is the only instance when you know that you have, for sure, some number of negative or positive real zeros. When you only have one sign change, you know that there has to be one such real valued zero and only one. If you had an odd number of sign changes that's higher, like 3 or 5, well, it could be 3 or 1, or 5 or 3 or 1. But when there's only one sign change, you know that there is one root of that kind. This does make a very good question for homeworks and quizzes and tests. So definitely be sure to know how to use Descartes' rule of signs to figure out the number of possible positive and negative real zeros. So that concludes this video on more information regarding the zeros of polynomials. In the next video, we are going to talk about rational functions and some properties of graphs of rational functions. Perhaps that will be a bit familiar to you, but perhaps not to some others. So if you have any questions or comments, be sure to reach out to me, send me an email, write me a letter, chuck something at me so you get my attention. But otherwise, until the next video, take it easy, guys.